Thanks for watching, and let's solve Laplace's equation using separational variables. So consider the equation uxx plus uyy equals 0 with u of x0 is 0, u of x pi is 0, u of 0y is y, and u of 1y is 3. And the way to visualize this is to have a very narrow plate. So consider a plate with, in this case, length 1 because of those conditions. So x in this case is from 0 to 1, and then y is from 0 to pi. And in particular, the four boundary conditions, they specify the temperature of that plate, but on all four sides. So what ux0 tells you is the temperature at the bottom. So here we know the bottom temperature is 0. U of x pi is the temperature at the top. U of 0y is the temperature on the left. So here we're saying the temperature starts at 0 and goes all the way to pi. And u of 1y is 3 is the temperature on the right. And by the way, don't worry if things are discontinuous because we just want to figure out the temperature in the inside of the plate. And by the way, very, very important, this technique only works if two parallel sides have 0 temperature. So either the top and bottom or the left or right. That said, in the next video, I will show you what to do if this is not the case. All right, let's get ready and separate variables. Okay, so part 1. So separation of variables. So as usual in this case, we will assume that u has a special form. So suppose u is a function of x times a function of y. We literally split the variables up. And of course what we want to do now is simply plug this into our PDE. So plug into uxx plus uyy is 0. So it's a bit of a shameless plug if you wish. So in this case, what we get is x of x times y of y with xx plus x of x times y of y, yy is 0. And then here all the x derivatives fall on the x function. So x double prime of x times y of y plus x of x times y double prime of y is 0. And then what we want to do, we want to again separate everything out. So let's put all the x's on one side, all the y's on the other side. And so now we end up getting x double prime of x times y of y is minus x of x times y double prime of y. And then let's divide the left-hand side by x and the right-hand side by y, and we end up getting x double prime of x over x of x is minus y double prime of y over y of y. And by the way, pardon the noise outside, it's raining like crazy. Hopefully you won't hear it too much. Now, here's a miracle as usual. The left-hand side only depends on x. The right-hand side only depends on y. So the only way they're equal is if they're constant. So this whole thing is equal to a constant, which we call lambda. In other words, the only way something good can be equal to something evil is if both of them are neutral. Now, just one little side remark. What about that minus? Well, the minus, you can put it wherever you want. Here, it doesn't really matter at all. Okay, and in this case, we end up getting two ODEs, which are very useful. So, step 3, the ODEs we get are simply x double prime of x is lambda x of x, and y double prime of y is minus lambda y of y. Now, here is the major difference between Laplace's equation and what we've done before with the heat and wave equation. Before, we always chose the x equation, but this time it depends. So, part 2, x or y equation And the reason I say or is because you always have to choose the equation that gives you zero boundary conditions. So always choose the ODE. The ODE with zero boundary conditions. Conditions, which it turns out in this case is the y equation, and here is y, no pun intended, because one zero boundary condition was u of x0 equals 0. But that implies, remember u is x times y, so x of x times y of 0 is 0, and then we can divide by x, and once again the reason is x is not the zero function, otherwise u is 0, so just pick a point where this is positive or negative and divide it out there. And so what we end up getting is y of 0 is 0. And similarly for the other case, x comma pi is 0. Then we get x of x times y of pi is 0. Once again, divide out by x and you get y of pi is 0. So in this case, it's the y function that has zero boundary conditions. And by the way, this explains precisely why we need two parallel sides to be 0. Otherwise, we won't get those zero conditions in this case. Perfect. So now what we do, we just consider the y equation with those boundary conditions. So welcome back to our 3 cases. So part 3. Three cases. So if you remember, so far we've dealt with the equation y double prime is minus lambda y with zero boundary conditions, and y of pi is 0. And if you notice, this is exactly the same problem we've been dealing with when we did our heat equation separation of variables, instead of minus lambda, instead of lambda. And so, in particular, I will not reinvent the wheel, I will just tell you the result. So, similar to before. And what we got was that the result is we had that the eigenvalues, so not lambda, but in this case minus lambda, was minus m squared, where m was 1, 2, 3, which in this case implies that lambda is m squared. So think 1 squared, 2 squared, 3 squared, etc. And the eigenfunctions are the sine functions. So y of y is, in this case, sine of my, where m is 1, 2, 3. So sine of y, sine of 2y, sine of 3y, etc. just the usual, and I will link a video again just showing this once again with the x equations. Good. Now we've done the y equation now, and now let's go to the x equation. Now part 4, let's deal with the x equation. Because what did we find so far? So far we had that x double prime is lambda x of x. But now remember we found what lambda is, namely it's m squared. So it's m squared x of x. And well, this is just your second order ODE, which we can solve using auxiliary equations. So r squared, in this case, is m squared. So r is plus minus m, which tells you that x of x is a e to the mx plus b e to the minus mx. Or technically a and b depend on m as well. Now, in theory, you could proceed now this way with this x. It's just, it will give you a little bit of trouble when you plug in the outer boundary conditions. So ideally what we want is a slightly nicer form of writing x. So note, let's find a nicer way. To write x, which you'll see in a second why it's nicer. But the reason is, ideally you want something where if we plug in x equals 0, we only find a, and the cool thing is we can actually do that using what are called hyperbolic cosh and sinh. So here's just a little primer on cosh and sinh. So definition, cosh of x is e to the x plus e to the minus x over 2, and sinh of x is e to the x minus e to the minus x over 2. And in particular, just one little thing, notice if you add both of them together, then you get cosh of x plus sinh of x, that is e to the x plus e to the minus x over 2, and then plus e to the x minus e of minus x over 2. Then e to the minus x's cancel out, and you end up getting e to the x. So in other words, you can write e to the x in terms of cosh and sinh. It's one thing. And last but not least, the only thing to know is that cosh is an even function and sinh is an odd function. So cosh of minus x is cosh of x, and sinh of minus x is minus sinh of x. And what we want to show now is simply that you can write your functions x in terms of cosh and sinh. So fact, x of x is a cosh of mx plus b sinh of mx for different constants a and b. A and b. And it's just a matter of combining all those facts here. So let's do this. Now, why is this true? Well, remember, we start with x of x is a e to the mx plus b e to the minus mx. Now remember, e to the x is a sum of cosh and sinh. So it's a cosh mx plus sinh of mx plus b cosh of minus mx plus sinh of minus mx. Now, remember, cosh of minus mx is just cosh of mx, and then sinh of minus mx is minus sinh of mx. And just expand this out, this becomes a cosh of mx plus a sinh of mx plus b cosh of mx minus b sinh of mx. And then all you need to do is combine like terms. So put the cosh together and put the sinh together. And you end up getting the following. This is a plus b cosh of mx and then plus a minus b sinh of mx. So if you just relabel this as a and relabel this as b, and you can still show those are arbitrary, you end up getting a cosh of mx plus b sinh of mx. So that's good. Our exponential functions are in fact really just cosh and sinh. And now you can finally see why this is so useful. So really, what have we shown so far? So fact, for every m from 1, 2, 3, the following solves Laplace's equation. Solves R of PDE, namely u of xy is x of x, y of y, which now x is a bunch of cosh, so am cosh mx plus bm sinh mx, and then y was just a sine of my. So remember, we got sine of my from our three cases, and then we got x by solving the x equation and by replacing exponentials with cosh and sinh. And now, as usual, all we need to do is take linear combinations, because this is almost like a basis of solutions, and now we kind of want to get a more general solution. So part 5, linear combo. So in this case, u of xy is now the sum from 1 to infinity of all those things. So am cosh mx plus bm sinh mx times sine of my. And now, there's two more things left because we have two more boundary conditions to deal with. So let's do that now. So part 6. I know, we're almost done, so there's two more parts. So let's do u of 0y is y. But remember, we have a formula for u of xy. So u of 0y is the sum from 1 to infinity of am cosh mx, mx in this case, so m times 0 plus bm sinh of m times 0 and then times sine of my. And here is where things get much, much nicer, because cosh of m0 is cosh of 0, and if you use the definition of cosh, you get this as 1, and similarly sinh of 0 is 0. So in the end, this just simplifies to the sum from 1 to infinity of am sine of my. And I really want to emphasize, we got this simplification because we use cosh and sinh. If you just use exponential functions, you would have gotten a big mess. So that was our main reason for using those hyperbolic trig functions. And so in the end, we know u of 0, y is y. So the question is, can we write y in terms of those sine functions? And the answer is yes, by using Fourier series. Because remember, y is between 0 and pi here. And so in this case, we can use hugging. So so y hugs the function sine of my. So integral from 0 to pi of this. And then sine hugs itself. That gives you pi over 2. So flipping, we get 2 over pi. And this is an integral we've already done when we did the sine series of x, and the result was 2 over m. And then minus 1 to the m plus 1. So that takes care of the ams. We know now what am is, and the last thing to figure out is what bm is. So let's do that now. And now let's do part 7. So let's do, I believe, u1y is 3. So same spiel as before. Let's plug in u1y. So that's the sum from 1 to infinity of am cosh m1 plus bm sinh m1, and then sine of my. And in this case, we get the sum from 1 to infinity of am cosh of m plus bm sinh of m, and then times sine of my. Which, unfortunately, it doesn't simplify as nicely as before, but notice this is still a sine series with this crazy coefficient. And this crazy coefficient, let's call it bm squiggle. So what we end up with is the sum from 1 to infinity of bm squiggle and then sine of my. And what we know, u of 1y is 3, so the first question is, can we write the function 3 in terms of the sine of ny's? And the answer is yes, once again using Fourier series. And by the way, so our plan of action is we will first solve for bm squiggle, and then using that formula, we will solve for bm, because we already know what am is. All right, and so let's do this once again. Let's use hugging, because this is on 0, pi. Once again, and we get the following. So once again, bm squiggle, you hug the function 3 with those sine functions. So in this case, you integrate from 0 to pi, and you divide by pi over 2. So 2 over pi. And the nice thing is, this integral you can evaluate. So that is 6 over pi. And then the antiderivative, I believe, is minus cosine my over m from 0 to pi. And then that becomes 6 over pi. And I believe minus cosine of pi m over m. And then plus cosine of 0 over m. And I believe, so the m factors out, so 6 over myself, so 6 over pi m and then minus 1 to the m plus 1, and I believe we get 6 over pi m. And I believe minus 1 to the m plus 1 plus 1. Which, if you want, you can simplify using even or odd. So if m is even, this becomes minus 1 plus 1, which is 0. So 0 if m is even. And then if m is odd, think m is 3, then this becomes 2, and this becomes 12 over pi m, if I'm not mistaken. 12 over pi m, if m is odd. Now, we're almost done. Unfortunately, not quite done, because we found bm squiggled, and now the last thing we need to do is find bm. Now we are almost done, because we solved for bm squiggled, but the last thing we need to do is to solve for bm. Because so far what we have, bm squiggled was am cosh of m plus bm sinh of m. And once again, we know bm squiggled, we know am, so all we need to do is to solve for bm. And so what we have now, bm sinh of m now becomes bm squiggled minus am cosh of m. And so in the end, bm is bm squiggled over sinh of m and minus am cosh of m over sinh of m. Which I know we can write as coth, but I don't want to scare you just yet. Now, all we need to do now is plug in our formulas for bm squiggled. So remember, bm squiggled was, I believe, 6 over pi m, myself, and I believe minus 1 to the m plus 1, and then over sinh of m, so 1 over sinh of m, and am, if I'm not mistaken, was 2 over m minus 1 to the m plus 1, and then cosh of m over sinh of m. Which, by the way, we can simplify just a little bit, because this minus and this minus, or this minus and this plus, just becomes minus 1 to the m. So this just ends up becoming 2 over m minus 1 to the m times that. And so in the end, we finally have our solution to Laplace's equation. And so what is the grand conclusion? In this case, u of xy is the sum from 1 to infinity of am cosh of mx plus bm sinh of mx times sine of my. And what is am? So where I believe am was 2 over m minus 1 to the m plus 1, and bm was, remember, that monster, so 6 over pi m, and then minus 1 to the m plus 1 times 1 over sinh of m, and I believe plus 2 over m minus 1 to the m, and then cosh of m over sinh of m. Which, if you want, you can write this in terms of even and odd, because it simplifies quite nicely. Because if m is even, all this becomes 0, and we're left with 2 over m, I believe. So 2 over m. And then cosh over sinh, if you want, you can write this as coth. You don't have to, but it simplifies this a little bit. So it's 2 over m coth of m if m is even. And if m is odd in this case, then this becomes 2, so we get 12 over pi m. And then 1 over sinh of m is ksh of m, so hyperbolic cosecant. And then this becomes 1, so plus 2 over m. No, if m is odd in this case, we get minus 2 over m, sorry. Minus 2 over m. And then coth of m. And if m is odd. Which in my opinion is quite nice. Okay, more importantly, what does that mean? So there's a nice interpretation because we have this metal plate. We want to figure out the temperature. What this solution tells us is the temperature, it oscillates in the y direction. So oscillates in y. So in the y direction kind of goes up and down. But then cosh and sinh, think of them as exponential. And this tells you that in the x direction, there is exponential growth. So exponential growth in x. So it's kind of interesting. It increases exponential in the x direction, but in the y direction, it kind of fluctuates ups and down. All right, congratulations on surviving this crazy Laplace adventure. If you like this and want to see more math, please make sure to subscribe to my channel. Thank you very much.